one of the reasons why decision trees are quite popular is the fact that they offer an easy way to perform feature ranking. And so the feature ranking problem is that where you have a data set and you would like to know which features contribute the most, to your problem, whether it's a classification problem or a regression problem. And you would even like to have a sort of a ranking, a sort of a relative comparison, of the features between themselves. Because that's really one of the aspects that make your models interpretable. You can give back to the users of that model some information about which aspects of their data set, of their problem, are the most informative for the question that they want to really solve. Feature ranking is not that easy to solve with other models, but it is really built in the decision trees. And here is how it goes. The more a feature is queried, the more important it is going to be. So the more is being used in decision nodes, in internal nodes of your decision tree, the more important it is. I can even say, the same thing in a more refined way. I can say the higher the drop in the impurity caused by a split on that feature, the more important the feature. So with that sort of idea, you can introduce right away this importance score. So importance score for feature J, so that's for a given decision tree. So you define it as importance of J to be sum by all the nodes M in which that feature was used, and you take the drop in the impurity of M. So this is going to be sum over all nodes M using feature J, or having a query on feature J. I also come back and I left some space in here. I want to say that this is typically defined as a normalized function because you want to have a way to compare between data sets with different size. So by having this normalization with respect to the number of data points, that's going to allow you to compare importances between data sets. And another thing that you also do, another type of normalization, is you want to have them relative to each other. Because otherwise, if you only look at this importance and it's let's say the number is 72 or something like that, it's going to be very difficult to interpret. But the moment you have this idea that you want to have in fact a normalized importance score, where you normalize with respect to the sum of all impurities or all importances for all features, then you are going to have them sum up to 1, and if you have this normalized importance to be, for example, 0.25, it means all of a sudden that this feature contributes 25% to solving the problem that you are solving. So that's going to give you a lot of advantages. So the normalized importance score for feature J this is just defined if I write it like normalized importance of J, you just say this is the importance of feature J divided by the sum over all the features of the importances of each feature. That's it. As you can see, it's already built in the decision trees. The impurities were, they're easy to calculate once you have the decision tree. One insight that I want to give also is that when you think about where exactly in your decision tree you have the biggest drops in impurity, it's not difficult to see that the biggest drops are close to the roots. In the root node and in the nodes immediately, below the root, that's where you will see the largest drops in the impurity, because that's where you have the largest and possibly the most mixed, versions of your training data set. So in other words, what this sort of importance score proposes is that the more a feature is used and the more it's used in the beginning of your decision process, the more important overall it's going to be.